Hi everyone. Today's video is going to focus on high-rate granular anaerobic reactors. Today we are going to learn about the specific tool that CRB Water has developed in-house for virtually analyzing the particle size distribution of granular biomass. This tool can rapidly determine if the granule particles in a sample have a higher chance of washing out from the reactor, causing major upsets. Moreover, this tool allows us to compare the granule sizes present in a sludge sample with the previous samples taken at the same site and overall industry averages. Let us start with a brief introduction of high-rate granular anaerobic reactors. High-rate granular anaerobic reactors must generate and retain dense granular biomass to treat waste successfully. This granular biomass comprises biofilm layers consisting of diverse microbial colonies working in a highly symbiotic environment. A cross-section of this anaerobic granule showing different layers of microbial communities is shown here. These reactors feed incoming wastewater in the bottom of the reactors to achieve maximum contact between a thick blanket of granular biomass and the incoming waste. Granules rapidly convert organic pollutants into small bubbles of biogas. These biogas bubbles lift the granules to the top portion of the reactor due to their buoyancy. The three-phase separator, also called as the gas solid liquid separator or GLSS device, located in the headspace of the reactor, separates granules, biogas, and clean water into three different separate streams. The collected biogas is sent to the biogas pipeline. The clean water, free of granules and pollutants, is sent to the effluent pipe. The degas granules must return to the sludge bed in the bottom of the reactor by gravity while finding their way through the upflowing water and newly lifted granules that are still attached to the formed biogas. The settling velocity of these sinking granules can be determined by Stokes' law as shown here. According to the Stokes' law, the settling velocity of a sinking granule is directly proportional to the square of its diameter. This principle means that smaller granule particles with lower settling velocities have a higher chance of washing out of the reactor through the effluent stream due to the high reactor turbulence and upflow caused by the biogas and the feed water. Such washout ultimately decreases the performance of the anaerobic reactor, leading to a reduction in the treatment quality. The biggest drawback of these high-rate granular technologies is that these processes are susceptible to frequent upsets due to changes in parameters such as organic waste load, temperatures, pH, presence of toxic chemicals, composition of waste, etc., causing these biofilms to break or the biomass to degranulate and leave the reactor. Once the biomass has left the system, the treatment performance suffers drastically, leading to hefty fines. If such changes happen gradually, it is challenging to determine it through effluent solids measurements. Getting reactor function back to desired levels is very tedious and expensive, since it can take up to 3 months to organically grow this lost biomass back to its original inventory. Operators of these systems often procure biomass from healthy reactors to restart their processes. Although this is the best course of action, such biomass is often scarce and requires high transportation costs. In such scenario, a tool is required to periodically check the granule sizes so any potential reasons for gradual sludge degranulation can be determined and eliminated, and potential upset can be avoided. We at CRB Water used our laboratory and data science expertise to develop an innovative solution to solve this problem. We call this solution as virtual sieve analysis for granules. Using sludge images, CRB Water has developed a procedure to analyze granule samples for their particle sizes rapidly. CRB Water's laboratory dilutes granular sludge sample at a predetermined rate and then takes pictures of these samples in a petri dish. These pictures are then used for particle size analysis. This analysis identifies granule particles from the sludge in the picture and measures the cross-sectional area of those granules using image analysis tools. This data for cross-sectional area of each granule is collected for each sample. Nominal diameter for each particle is calculated using this equation. The high volume data is appended to a database maintained by CRB Water using in-house software. This database is used for plotting particle size distributions of the granules for various locations using a proprietary dashboard. Data are plotted in the form of histograms, which then are compared with previous histograms for the same sample location, and a combined histogram for all the locations representing a particular industry. Such thorough comparison enables conclusion regarding the changing nature of granules to detect problems much earlier. We have perfected the method so that the entire data analysis process takes less than 5 minutes, as shown in this animated clip. Within 3.5 years, CRB's particle size database has grown to have more than 3.4 million data points. And it is growing every day to facilitate more comparisons. The above-mentioned tool was used to periodically monitor the particle granule sizes at a full-scale industrial wastewater treatment plant. Table 1 shows the series of photographic images taken at random intervals for the sample from a reactor location. The analyzed images and comparative histograms indicating particle size distributions for each sampling instance. So here are the dashboard specifics. The dark lines in the histogram charts indicate the cumulative percent of total granule area for each sample. These lines are also called Pareto curves. The red-green color interface midpoint was set at 0.75 millimeter. That means the particles that are smaller than 0.75 millimeters are represented by red color, and the particles with larger diameters are indicated by green color. The numbers mentioned along the Pareto curve, or the cumulative percent area curve, indicate the sample's granule particle sizes representing the 25th, 50th, and 75th percentile of the total cumulative area respectively. The bin size indicates the interval particle diameter range used to create different buckets or bins for plotting the histograms, which is currently set at 0.25 millimeter in this diagram. The red color in the histogram shown in the figure increased from July 2020 to May 2021 samples. It is noteworthy that all the samples after September 2021 indicated smaller particle sizes than the industry averages for that particular industry. Eventually, the reactor experienced a significant upset in terms of sludge washout in May 2021, as seen by significantly smaller particles in the sample collected in May 2021. Our tool had predicted the gradual reduction in the particle size at the industrial site. Perhaps this pre-warning data can be used to detect gradual sludge degranulation to prevent future upsets. A gradual reduction in the particle size of the granules occurred, ultimately resulting a reactor upset as determined by the last sampling instance. A naked eye inspection cannot typically observe such a minor change in granule sizes. Whereas the virtual sieve analysis for granules tool developed by CRB Water can detect this granule size reduction, it could have been used as a warning sign for troubleshooting the reactor to prevent this upset. Well, this concludes this video on granule particle size distribution tool, and I hope you feel as thrilled as we do about the possibilities of predicting and preventing future upsets using such innovative tools. If you have any further questions regarding the contents of this video, please feel free to contact us using the contact details given below. Thank you so much for your attention, and I'll see you in the next video. Bye.